Hello again, I'm Tsui from Jepic. My second lecture is about principle of distribution line in Japan. In this lecture, I'll explain about the basic part of the electric power distribution system in Japan. This is a table of contents of this lecture. I think there are lots of differences in power distribution system between Indonesia and Japan, such as supply voltage, protection system, and so on. So I'll explain about standard distribution facilities in Japan at first, then I'll talk about protection systems or equipment and maintenance of distribution line. Among what I'll talk about, there might be something that's already used in Indonesia, but I expect you to compare the facilities in Indonesia with ones in Japan and to acquire something useful to improve sci-fi and SciD. By the way, this lecture is made based on what I had experienced in my original company called Hokuriku Electric Power Transmission and Distribution Company. Before the main contents, please let me introduce myself and my company. Once again, I'm Tsui from Jepic and in charge of this lecture and this seminar. Let me introduce myself briefly. Now I'm dispatched to Jepic from my original company, Hokuriku Electric Power Transmission and Distribution Company. I joined Hokuriku Electric Power Company in 2008 and I assigned to distribution department as an engineer. First, I take a training for about 3 months as a distribution network engineer, then I worked as a maintenance staff doing mainly patrol, inspection, and so on. Then I was assigned to design division and did pole site negotiation, technical calculation and drawing blueprints and so on. After that, I engaged with tasks related to construction. Then I was dispatched to this organization, Jepic, in power transmission and distribution business in the northern central region of Japan. This area is called Hokuriku. In this area, there are the ocean that joins world's most beautiful bays club and a cafe said to be one of the most beautiful in the world near the headquarters. So when you come to Japan, I recommend you to visit our Hokuriku area. As I explained in the lecture of Outline of Electric Power Industry in Japan, our company was legally unbundled as a subsidiary from Hokuriku Electric Power Company, which had been a vertically integrated company. Hokuriku Electric Power Transmission and Distribution Company employs about 2,003. This table shows the classification of distribution system in Japan. The voltage classification is defined by a law regarding electric power facility, and the voltage is sorted by DC and AC, as you know. In Japan, as for the DC, 750 volt or less is low voltage. Above 750 volt and 7000 volt or less is high voltage. Above 7000 volt is ultra high voltage. As for the AC, 600 volt or less is low voltage. Above 600 volt and 7000 volt or less is high voltage. Above 7000 volt is ultra high voltage. Most of the distribution line is operated at nominal voltage 6.6 kV by 3-phase 3-line system. Ultra high voltage distribution line of high voltage overhead distribution system in Japan. For the purpose of improvement of supply reliability and area power failure recovery, multi-divided, multi-connected system is popular in the configuration of 6.6 kV distribution system. One distribution line is divided into several sections, and each section is connected to its neighboring feeder so that each section can be energize each other. When a power outage occurs, distribution automation system identifies the defected section, and the other sound section can be supplied from neighboring feeders. The detail about distribution automation system will be in another lecture. In the region with a few number of customers, there are fewer neighboring feeders and the connection points decrease compared with urban area, so the supply reliability might get lower. This picture is an example of a 6.6 kV standard electric pole with transformer in Hokuriku region. Basically, the equipment with higher voltage is assembled so that it comes to the higher position. I'll explain about the equipment used for power distribution from the next slide. First, I'd like to talk about the concrete pole, which is the main supporting structure of overhead distribution line. The table shows the standard types of concrete poles in Hokuriku area. The most commonly used pole is 14 meters long. When it's necessary to put two feeders on a pole or to keep a distance from other structures, 16-meter pole is also used. When a concrete pole can't be constructed by some site matters, like difficulty in transporting poles to the site, assembling type iron poles are sometimes constructed. A concrete pole has a taper shape and it's normally 1/75 centimeter. For the purpose to avoid being a disturbance of traffic or site matter, thinner types like 1/110 centimeters or 1/160 centimeters type are sometimes used. The numbers with parentheses are strain type pole, reluctantly used when a stay wire can't be put for the site reason. These concrete poles are pre-stressed concrete poles whose reinforced steel inside are tensioned in its manufacturing so that the pole becomes stronger against cracks. The standard distance between poles is about 40 meters or 50 meters, and which type of pole should be used is decided considering the future demand, cost or site situation, etc. Then doing appropriate calculation, the supply reliability is kept. Next slide is about high voltage wires. In Japan, it is stipulated by law that high voltage wires should be insulated, and the most common used one as an insulation of high voltage conductor is outdoor cross-linked polyethylene. Copper or aluminum are commonly used as a conductor, but in the past, lots of disconnections of copper wires had happened due to the stress corrosion. So, as a countermeasure against this, low wind pressure aluminum wire was developed and has been introduced. Aluminum is unlikely to rust, so the stress corrosion is prevented, but it has a larger resistance than copper, so the diameter of conductor becomes larger. Then its wind pressure also gets stronger. Low wind pressure wire has a polygonal surface so that its wind pressure can be reduced. The table shows the types of wires used in Hokuriku area, and the ones in blue are currently used as standards. Allowable current of 240 square is 512 amperes, equals about 5,600 kilowatt. That of 120 square is 308 amperes, equals about 3,400 kilowatt, and of 5 millimeters is 142 amperes, about 1,500 kilowatt. 5 mm wires are used in branch lines with small load, but when it's near a substation, 120 square wires are used so that disconnections don't happen by a large short circuit current. Next one is about switches. Switches are sorted into manual type and automated type. Automated type is a part of distribution automation system, DAS, and we also call it a sectionalizer too. The detail of DAS will be in another lecture, so I don't explain about it here in detail. A manual switch is operated by its rope at the site. On the other hand, an automated one can be controlled remotely from an office. Automated switches are installed so that each section divided by them has a certain demand, and where a manual switches should be installed is decided, considering the maintainability of distribution line. For example, the place that's considered to be effective for power outage recovery or a branch point of a long branch line. Where and how many switches should be located is closely related to the number and duration of power outage customers in an outage. So I think that's an important point to improve SciFi and SciD. Switches can turn on or turn off electricity supply, so it's also important to prevent power outage due to long operation of switches. This slide is about a transformer. As a supply transformer on poles, a single-phase transformer is mainly used. When there's a power load customer with three-phase line, two single-phase transformers are connected with V connection to supply to them. The picture is the one that two transformers, 30 kVA, 5 kVA, are installed. As I explained before, 6.6 kV is mainly used for high voltage distribution line, and 100 or 200 volt is used for low voltage. The transformer ratio is usually 6.6 kV to 210 or 105 volt, and as shown in the figure, at the low voltage side, a transformer has three terminals. One of the terminals comes from the middle of the secondary coil so that it can supply single-phase line. And also, the two transformers might have different capacities, but the same specification. Low voltage distribution system is three-phase 4-line. Drop service wire is connected to the low voltage system according to the customer's type. The transformer for lighting load has an earth as shown in the figure. This earth is put for prevention of abnormal voltage from invading to low voltage line, which might cause electric shock to customers when the high voltage accidentally contacts the low voltage side. In this page, I'll explain about wires used in low voltage lines and drop service lines. As for low voltage line, in Hokuriku area, copper conductors are commonly used, but in other electric power companies use aluminum conductors too. As shown in the upper table, wire size used as low voltage lines are 4 mm, 5 mm of single wire, and 60 square stranded wire. The picture is an example of how the low voltage line is installed. In this picture, the order of the low voltage line is the same as the connection figure in the previous page. The lines L1, L2 is usually the thickest. This is because the current of both single-phase and three-phase flow through L1 and L2 line. Vice versa, P line is usually thinner than L1 and L2 because only three-phase currents flow. E line is normally one side smaller than L1 and L2 as long as voltage drop doesn't matter. And also, if only E line gets disconnected, over voltage might be supplied to lighting load customer, so it's located between other lines so that only E line doesn't get disconnected. As for drop service wires, the stranded wires like this figure are used called DSDV wire. There are two conductor type and three conductor type. DS represents double structure, which has two layers in its insulator. As you can see in the cross-section illustration, inner layer is black, which has a higher weather resistance, and the outer layer is a layer with colors black, blue, and green to see the phase. In the past, its insulator had consisted of single layer with color, but compared with black, color insulation layer have lower weather resistance, so they deteriorated more easily, and resulting in short circuit and disconnection. So this kind of wire was developed and has been installed. By the way, it's off the topic. When I entered electric power company as a distribution engineer and was taking a recovery training of DV wire disconnection, I had a hard time making a beautiful stranded reconnected wire. I remember that my trainer said, if my recovery work looked bad, it might put a bad impression on customers. So it's not good enough just to reconnect it, but have to do it with a beautiful finish. Next, I'd like to talk about the equipment connected to high voltage customers. The same wires as high voltage line are used as high voltage drop service lines. The supporting structure which receives drop service line belongs to each customer, which can be a pole, a wall of a building, and in any cases, it has to be meet technical standard. A switch called path is installed at the border point of electricity service, and when a failure of the customer facility occurs, it can cut from power grid. Path can detect a ground fault and a short circuit, and in case of a ground failure, path can cut itself before the CV of substation trips. On the other hand, in case of a short circuit, path cannot break a short circuit current, so after detecting a short circuit current, CV of the feeder once trips. Then electricity is sent again, but path won't turn on. Meter is installed combined with VCT in the customer side of path. It usually measures kilowatt-hour, kiloval, and demand. In general, a service contract of high voltage customer is decided based on its demand, and there is a discount if they improve their lagging power factor. Most of the high voltage load is lagging, so the customers install capacitor to compensate it. This figure shows a standard facility of a general house. High voltage electricity is stepped down by transformer and supplied to customers through low voltage line and drop service line. A receiving point of drop service line is the border point of electricity service. A meter contract breaker is normally installed in the customer side, but they are the electric company's possession. In recent years, smart meters have been installed, and they can be read and controlled remotely. We can remotely get metadata every 30 minutes, and the calculated every 30 minutes kilowatt-hour is offered to retailers. Next chapter is about protection systems of distribution line. Distribution line consists of high voltage and low voltage parts. Since they are installed in a wide area compared with other electric power facilities, we try to reduce failures by improvement of equipment, enhancement of maintenance or inspections. However, once a failure has occurred, it will be very important to prevent outage from spreading as well as to prevent the public from being injured. The table shows the major protection systems. Blues are for overcurrent. Reds are ground fault. Relays are installed in substation, which protect an entire feeder, and other fuses are protecting its load side and prevent failures from spreading into upper grid. From this slide, I'll explain how protection relays in substations work. Here, I'll explain about the types of protection relays in substations. Overcurrent relay is a relay for overload or short circuit. This relay has two CTs, which is installed to every feeder and usually monitored two phases of the three. This is because overcurrent is a phenomenon that always involves two phases or more, so monitoring only two phases is enough to detect overcurrent. Since overcurrent might cause conductor melting or damage on equipment, its work time to trip CV is set shorter than that of ground fault relays, and distribution line equipment are designed to bear a fixed short circuit current, and distribution line is also designed not to exceed the fixed value. Blue ones are for ground fault. Ground direction relay is also installed to every feeder, and when a ground fault occurs, it detects its ground fault current comparing with ground fault voltage and judge whether the ground fault occurs in each feeder or not. Ground over voltage relay detects ground fault over voltage. Ground directional relay and ground over voltage relay are combined to identify in which feeder a ground fault occurs, and then makes CV trip. and its work time of CV trip is 0.8 seconds. Ground over voltage relay is also used as a backup protection. In the case that ground fault over voltage is detected but not ground fault current like a fine ground fault, being combined with ground fault select relay, each feeder is made to trip one by one until ground over voltage not being detected. Reclosing relay is a relay to energize automatically feeder after CB is made to trip by either relay. Since there are some of instantaneous fault like tree touching, this method is used. Furthermore, combination of re-energization and DAS detects the defected section. This is a figure which shows how the relays of distribution line work. As shown in red, overcurrent of overload or short circuit is detected by OCR, and CV is made to trip in 0.2 seconds after overcurrent detection. Blue shows the protection relays for ground faults. DGR works in 0.2 seconds after it detecting ground fault current, while OVGR works in 0.8 seconds. So, if ground fault goes on for 0.8 seconds, both relays works and CB will be made to trip. If, for example, a spontaneous ground fault like tree touching occurs, CB doesn't trip, but DGR does. In the case like this, we patrol that feeder to prevent power outage. There are two OVGR. One is used together with DGR and to identify a defective feeder, and another is used together with GSR as a backup protection for ground fault. GSR work when a ground fault current is too small to detect, but only OVGR works. When GSR works, it makes each feeder trip one by one until ground fault voltage not being detected. After the defective feeder is identified, other sound feeders will be energized again. REC recloses CV in 15 seconds after CV trips. If outage happens during re-energization, this relay tries to energize once again in 60 seconds. This figure shows a model of standard connection of distribution line with single-phase ground fault current, represented by blue arrows. Once a single-phase ground fault happens on feeder A, the voltage to the ground of the defected phase becomes 0 volt. Then the charge current according to its line capacitance flows from the sound phase into the defected phase, and this current is the ground fault current. The directions of the fault current, so to speak zero-phase current, are different between feeder A and B at the DGR point. The earth voltage transformer, which is installed to each distribution transformer, measures the ground fault voltage. Some of the ground fault current flows through the earth voltage transformer, and the voltage caused by this current is the voltage of resistance Rn put in the secondary side of open delta. And this voltage applied to Rn is detected as a ground fault voltage. In the case a distribution line expands in a long distance and it's supplied to both urban area and rural mountainous area, a branch line breaker is sometimes installed to keep the supply reliability. Branch line breaker can detect both ground fault and overcurrent fault of its load side and break itself before CV of feeder trips. Then it automatically energizes again in a certain time after it trips, as if it were a small substation. As shown in the figure, branch line breaker is installed at the border point between urban and rural area of a distribution line, which expands from the area which has important customers like hospitals to mountainous area with few load and higher risk of failure. When a failure occurs in the road side of it, Branch line breaker can localize the outage area and prevent it from expanding to its supply side. As distribution line expands in a long distance, the line impedance also becomes larger. This sometimes makes the short circuit current too small to detect at substation. In this case, a branch line breaker with a function only to detect short circuit current is installed. Next is the protection for transformer and low voltage line. Transformers might be burned out by various causes such as lightning, short circuit of low voltage line, and so on. Burnout transformer might cause an outage of not only the customers connecting to the transformer, but also the entire feeder. So it's very important to prevent the outage from spreading to upper grid. High voltage cutout fuses are installed between high voltage line and transformer as shown in the picture for the protection of overcurrent. On the other hand, when a ground fault occurs due to an insulation failure of a transformer, it will be detected by ground fault relays in substation, resulting in an outage of the entire feeder. This fuse protects not only transformers but also low voltage line, and by insertion and removal of the fuse, it's possible to energize or unenergize the transformer. When a transformer is unenergized by this fuse, a spacer as shown in the slide is inserted to make it clear whether the trans is energized or not. This is because some accidents, like being shocked, had happened in the past due to misrecognition. This picture shows a wire-shaped fuse which is installed at the outlet of each drop service line. This fuse protects from overcurrent. This is attached to two of the three phases of each drop service line. An attached line is the earth phase. This is because if the earth phase is disconnected, an abnormal overvoltage will be applied to the customers, causing the customer's equipment to break. The protection range of high voltage cutout fuse and wire-shaped fuse is as shown in the figure. Transformers and low voltage distribution lines are protected by high voltage cutout fuse, and drop service lines are protected by wire-shaped fuse. From here, I'd like to explain about the lightning protection equipment. Among the causes of power outage in the distribution line, lightning accounts for a certain ratio every year, so taking appropriate lightning protection measures is very important. Main lightning protection measures are as shown in the table: ground wire, lightning arrestor, arcing horn, ZNO supporting insulator. Ground wire is usually a steel wire which is installed on the top of the distribution equipment and protects electric poles or lines from direct lightning stroke. Even if the lightning doesn't strike distribution equipment directly, induced lightning surge may cause damage. But it's expected that lightning surge can be divided into conductors and ground wire so that the surge current of induced lightning that invades conductors can be reduced. Earth is put every 3 or 4 poles to lead the lightning surge to the ground. And ground wire is usually installed together with lightning arrestor and prevents the damages by lightning surge. This slide is about lightning arrestor. When a lightning surge invades into line conductors, lightning arresters can release the surge to the ground for the purpose of the prevention of flashover, and then it can cut off the follow current when the surge voltage reduces down to a certain value. In this way, lightning arrestor protects distribution equipment from being damaged. This function is realized by the nonlinear characteristics of zinc oxide elements inside the lightning arrestor. When a lightning surge is passing by where a lightning arrestor is, the insulation resistance of a lightning arrestor between line and the ground becomes low enough to release the surge to the ground, and then, once the surge voltage reduces below a certain value, its insulation resistance immediately recovers to cut off the follow current. In the case of a strong lightning, a large surge exceeding the capacity of a lightning arrestor might flow, resulting in a burnout of lightning arrestor, but installing together with ground wire can reduce the surge. Lightning arresters should be installed within force spans around 200 meters. In addition, at the end of the line, surges reflect in the same phase and the surge amplitude gets doubled. So larger capacity lightning arresters need to be installed at the end of a line. This slide explains how an arcing horn works to prevent wire disconnection by flashover. Ground wire and lightning arresters are to protect the entire equipment of distribution line from lightning surge by releasing the surge to the ground. On the other hand, an arcing horn is mainly to prevent disconnection of lines by flashover. If lightning surges invade conductors and flashover between conductors and metal arm occurred on more than two phases, the flow current of flashover might transit to a short circuit through the metal arm, resulting in disconnection. To prevent such a case, arcing horns are attached to insulators as shown in the picture. An arcing horn consists of a ring-shaped metal part and a part containing the NO element. The discharge of a flashover can be separated from the insulator's surface, and its flow current can be cut off like a lightning arrestor before the flow current transits to a short circuit. By the way, omitting one-phase arcing horn of three phases has been applied to cut down the cost because it said that the failure suppression effect is almost the same. Japanese distribution lines are basically known as the system, and its ground fault current is small, so the flow current of a flashover of just one phase without an arcing horn disappears by itself spontaneously. This is a ZNO supporting insulator. This equipment is installed as a supporting insulator which holds drop wire from high voltage line to transformer. As in its name, it has a zinc oxide element in it and prevents lightning surge from invading into a transformer. I'll explain briefly about the design of lightning protection equipment. The trunk line basically has ground wire. Lightning arresters are installed within force spans or at the pole with some equipment like switches. On the pole with transformers, ZNO supporting insulators are installed. When there are two transformers in the V connection, ZNO supporting insulators are attached to all the three phases. On the other hand, when there's only one transformer, two ZNO supporting insulators and one arcing horn is attached to cover all the three phases. If the pole has no equipment, arcing horns are attached to two phases. Lightning protection equipment are installed so that all the poles have either kind of them. Next subject is salt pollution protection. In the area near the sea, distribution equipment might be polluted by the salty water blown away from the sea, and it sometimes causes a failure due to a poor insulation or deteriorated equipment. In such area, salt pollution protection should be considered when constructing facilities to ensure the supply reliability, or the facilities might deteriorate more quickly. The figure and pictures are a comparison of an anti-pollution insulator and a normal insulator. The right one is an anti-pollution insulator which has a longer creeping distance than the normal one, so that even if its surface is polluted, dielectric breakdown is more unlikely to happen. The other equipment used in such area are also designed to withstand pollution. For example, high corrosion resistance plated equipment have been introduced to keep the reliability. By using such kind of equipment, they get more unlikely to rust, and the mean time of repairing can be expanded, as well as the supply reliability can be improved. In addition, some equipment like transformer or high voltage cutout, the ones with lead wires are used, different from normal types, so that the leak current can be suppressed to prevent a failure. The next chapter is maintenance of distribution line. First, I'd like to talk about the legal state of maintenance of electric power facility. In Japan, electric power utilities are regulated by the law of Electricity Business Act. This law is mainly to protect electricity users, to achieve sound development, and to assure public safety. And based on this law, Ministerial Ordinance on Electrical Equipment Technical Standards is stipulated. This ministerial ordinance defines technical standards regarding electric power facilities, and we have to strictly comply with them. And Electricity Business Act requires electric power utilities independent safety measure, and each utility has to establish safety regulation and notify METI of it. By the way, METI is a supervisory ministry of electric power industry. Electric power utilities have to decide the duties, organization, education for safety measures in the safety regulations. Electric power facilities are operated and maintained according to these safety regulations. In this slide, I'll explain briefly about the patrol and inspection of Hokuriku Electric Power Transmission and Distribution Company. The power equipment deteriorates, being exposed to severe nature, so we have to find the defections or the risks of power outage and repair them in advance. And also, there are enormous number of equipment. The equipment deterioration should be classified according to its state so that the effective repair plan can be formulated. By patrol and inspection, information needed to formulate plan is also gathered. The table shows the types of patrol and inspection. The frequency is defined in safety regulations, which is notified to METI. Periodic patrol is done every 5 years. In periodic patrol, all the distribution equipment of each electric pole, mainly overhead lines, are visually inspected every 5 years. The deterioration state are classified according to their degree. By-purpose patrols are conducted as necessary, taking into consideration the season, weather, characteristics of area, and the influence of a failure. For example, depending on the season, the ivy might grow up to the top of a pole, leading a ground fault. A patrol for ivy is done from spring to summer. There are other cases such as a patrol for bird nesting, a patrol after strong winds, an emergency patrol in an outage, and so on. Inspection targets specified electric facilities like SVR, underground device, etc. in a certain period. Depending on target, facilities are inspected according to it closely by not only visually but also using measurement device. The information acquired through patrols and inspections are accumulated and used for formulating repair plan. Patrols and inspections are the basis of maintenance. Improvement of efficiency by using digital technologies is a key issue at the moment. This slide shows the concept of patrol system. When we patrol, we register the conditions, degrees of items that need repair into a mobile device. This data will be transferred to the database of patrol system. Repair order is done after its registry, and then repair design, order, and work will be conducted. And also, according to the accumulated information, repair plan is formulated. In this slide, I explain about measures against tree. Distribution lines often pass through areas with lots of trees, and in such cases, a failure might happen due to disconnection by fallen trees or a ground fault by damage of insulation. As a maintenance of such facilities, there are two types of countermeasures. One is measures of facility, another is tree felling. Which measures should be taken is determined taking into consideration of cost or maintainability, etc. One measure of facility is route change, which I think is the most effective. In this case, Facilities like poles, lines, etc. are newly constructed, so the cost will be higher than other measures. But when route change is chosen, there's usually newly constructed road and its maintainability gets well. Another measure of facility is to upgrade equipment, for example, using an anti-wear wire which is stronger against friction with trees. The cross-section of anti-wear wire is shown in this figure. It has wear layer and wear detection layer as additional layers, so it's less likely that the conductor is exposed than normal insulation wires. If it's been worn out and the yellow wear detection layer is exposed, we can recognize it's time to be replaced. The picture in the right shows the situation of tree felling. When we don't or cannot take facility measures, tree felling should be conducted to keep a certain distance between lines and trees so that a failure doesn't happen. When felling trees, we negotiate with the landowner, pay compensation expense to them. Basically, we try to cut the root of trees, but not all the owner agree to it. In such case, only branches are cut. We manage such places and cut branches regularly to prevent power outage. And also, preparing for distribution failure, engineers in distribution department take regularly training of tree felling and learn how to use tools for tree felling like chainsaw and so on. As an initiative for the protection of the public safety and prevention of a power outage, I'd like to talk about attachment of protecting equipment. Since distribution lines expand anywhere, there might be obstacles of other works such as building constructions. If construction work was conducted over the energized lines, it might cause a public disaster like being electrocuted. So, for the protection of the public safety, electric power companies advertise construction firms to apply for in advance. In the example picture, a protecting tube with yellow and black is attached. These protecting equipment are temporary items, and after construction work has been done, they'd be unattached. Next, I'll talk about countermeasures against bird nesting. Crows, very common bird in Japan, often nest on electric poles from March to the beginning of June every year. Their nests sometimes contain metal wires, which can be cause of power outage, so we need to patrol to find and deal with them. Even if we remove the nest from the pole, they tend to nest again on the same pole until they lay eggs. So when the risk of power outage is low, we leave the nest until crows lay eggs. The crow which grew up in the nest on an electric pole is more likely to nest on a pole, so although we leave the nest, we remove the eggs before them incubating. By the way, we have to get legal permission to remove wild animals' eggs in Japan. After the crow lay eggs, we eventually remove the nest. During this season, a lot of manpower is devoted to this work. This picture is the one when stork nest on a pole. Stork is a kind of symbol of happiness because it's said to deliver babies, and designated as a natural monument in Japan. They seldom nest on a pole, but in the case that it nested on a pole in Hokuriku area, we made temporary alternative supply route and stopped electricity on the pole to protect the nest. Such activity is also important to improve customers' impression on electric power companies. When a construction work like upgrading equipment is conducted, it's often necessary to stop electricity. Here, I'd like to explain about a method to localize the outage area for work by using some temporary equipment such as switch or generator vehicle, etc. Supposing a construction work was conducted in the light blue area and we tried to stop energizing to this area by permanent equipment. Wide area, including the area with no work, would be in power outage. Therefore, by using a temporary switch or generator vehicle, the supposed outage area would be localized. If there was no work regarding low voltage equipment, it would be possible to continue to supply electricity to the low voltage system in the outage area by using low voltage generator vehicle. Using these kind of methods, it's possible to localize the power outage area and reduce the number of power outage customers due to construction work. These are the pictures of the method I explained in the previous slide. Two upper pictures showed the situation to install a temporary switch and the line cut between poles. Before the line being cut, a bypass route is formulated by temporary cable and switch, as shown in the yellow line. Then the line will be cut in the middle of the span between poles by giving the tension of the line to a special equipment. The upper right one shows how to reconnect conductors in this method. This work is conducted by indirect live line work, which is done by using insulated operation stick for the purpose of the safety of workmen. The lower photo shows the high voltage generator vehicle is being installed. There are high voltage and low voltage type of generator vehicle, both of which can transfer the load from the commercial power source to the generator without power outage. These generator vehicles were introduced for emergency supply, but they are also used to localize the area of power outage when construction work being done. Next, I'd like to explain briefly about the recovery procedure of a failure. When an outage failure occurs, how quick we can recover is an important factor to improve SAIFI and SAIDI. Once a failure occurs, distribution automation system will identify the defected section and the other sand section will be energized automatically. After identifying the defected section, we further divide the defected section into some sections by manual switches to clarify where the fault is. I'll explain a little more concretely with this illustration. The example that a ground fault occurs in third area. The first area, surrounded by blue, would be the outage area after distribution automation system identified. When recovery workers arrive, they patrol roughly to energize again while dividing the section by manual switches. The area divided by manual switches would be tried to be energized one by one. Light blue line would be the first section where trial energization is done, so they at first do rack patrol on this line. Rack patrol is a patrol to confirm if there's not any risk to the public, such as an electric shock, line disconnection or something like that, and it's done as quick as possible. In this case, since the cause is in third area, the trial energization to the light blue line from an automated switch would be succeed and the outage area would be second area. Next, the light orange area is the area to which the trial energization should be done. In the same way as the light blue line, that area would be patrolled roughly, but the trial energization would be done by a manual switch, different from the previous one. Automated switch of distribution automation system can turn it off by itself before CV of the feeder trips, if it detects a ground fault when it turns on. On the other hand, a manual switch doesn't have such function. So when we do a trial energization to an outage area by a manual switch, we turn it on and off manually and instantaneously within 0.8 seconds. I mean, we turn it on but immediately turn it off again before CV of the feeder trips. The CV trips in 0.8 seconds if there's a ground fault, but in 0.2 seconds the ground fault current relay works. By monitoring whether that relay works or not, we can confirm if there's a failure in the area where we try to energize. Then, the outage area would be finalized in this procedure. When the cause of a failure is difficult to discover by visual patrol, we think how quickly we can finalize the outage area is one of the key points. By the way, if the cause is a short circuit, we have to be more careful not to make the damage of defective equipment severer by a trial energization. After the outage area was finalized, that area would be patrolled, but some causes might be difficult to find visually. In such cases, we use the ground fault detector to find where the ground fault is. As shown in the figure, a ground fault detector is connected to the high voltage line and to the ground. It applies a DC pulse voltage to the high voltage line, and the pulse flows through a ground fault circuit, formulated by a ground fault detector, high voltage line, a ground fault point, and the ground. We can detect this pulse going through this closed circuit by using CT receivers. These CT receivers react only when it's put to the closed circuit, so we can see where a defect point is. In this example, it reacts at the point of lead wire from a transformer, so we can judge that transformer is defective. By the way, in the case that a transformer then energize high voltage line again. After that, the defective transformer would be replaced. After the cause of a power outage is identified, we have to repair it as soon as possible. Depending on the types of causes, we need to arrange the electric construction workers, but we, as electric power distribution engineers, are trained to repair the equipment by their own, as long as it's not a too serious damage. In preparation for failure recovery, distribution department engineers regularly take trainings of failure recovery to improve their skills to repair equipment. These photos show the safety and skill competition held annually in my company. By the way, the man riding an aerial work platform is me. I won the first prize at that time in 2011. The content of the competition is different every year. When I participated in, the contents was based on the assumption that due to lightning, one aluminum wire of 120 square was disconnected. High voltage cutout was damaged, and one transformer went wrong. The recovery work was completed within about 90 minutes by a group of 4 people, 1 leader and 3 workers. I prepared some short movies of the competition, so please take a look at them and feel in what kind of atmosphere the competition is conducted. The first movie is a station of hazard prediction activity, which we do before works.
ワンポイントは電線固定をしていく。よし。チーム行動目標。
電線切断時は川原市電線を固定して行おう。よし。
ワンポイント。
電線固定よし。電線固定よし。電線固定よし。
一度サイズ確認。よし。
一度サイズ確認よし。
今日もゼロサイズ行こう。よし。
今日もゼロサイズ行こう。よし。
Next one shows that I'm just recovering a disconnected wire. Last one is that the transformer is being replaced. Next, I'd like to introduce the efforts by electric power companies in some cases resulted in a long-time power outage in wide area. In the case of large-scale outage by natural disasters, electric power utilities dispatch recovery personnel to the suffered area. Generator vehicles, pole set vehicles, and line workers are dispatched to outage area to do urgent electricity supply to important locations such as evacuation shelters or to support restoration of electric power facilities. In the past, support like this has been done based on the request from the suffered electric power company, but in recent years, push-type support are being done. This means that if a serious damage in the neighboring area is expected, electric power companies voluntarily establish support system before the request, and they let support personnel on standby near the suffered area. Electric power companies have agreements with other utilities such as municipality or other industry companies for the case of disaster recovery. For example, electric power companies cooperate with a company managing highway or running large shopping malls, and they provide a recovery base or some materials. These make it possible to establish recovery system promptly and concentrate on recovery. These pictures are taken during the recovery from Typhoon 15 in 2019. As shown in this picture, dispatched personnel gather at a recovery base and they are ordered to go each side. In order to welcome a large number of people smoothly, training which involve each electric power company are also carried out regularly. And that's all for my lecture. Thank you. Terima kasih.